Hi everyone, my name is Chris Vaca, theoretical physicist here. So what I wanted to do today was do two calculations of electric fields that take advantage of the principle of linear superposition for static charge distributions. The two problems that we're going to be working on today, let me go ahead and show you. First, we're going to be calculating the electric field a distance d away from the end of a charged rod with a charge density lambda spread uniformly across its body with a distance L. The second charge distribution for which I would want to calculate the electric field for, that's going to be this half ring here of charge that has, once again, a charge per unit length lambda. And what we want to know is what is the electric field created at the center of this ring. Again, these problems take advantage of the techniques that you've learned in your introductory electromagnetism course when it comes to calculating electric fields. And let's go ahead and knock them out right now. So let's start with the long straight rod first. So, long straight rod problem, classic problem. Again, as a student, you should always be asking yourself, why should I give a damn about long straight rods? And so a quick answer to that is, again, a little review of what electric fields do, right? Electric fields tell you about the forces that charged particles feel, right? So long straight rods that are charged up, where do they happen in nature? Where do they happen in tech, right? Again, two quick examples that come to mind based upon my background is long straight rods that are charged up, very sort of rough approximation to charged polymers that exist all across biology and in nature. Again, very famous charged polymer, DNA, right? Has a negative phosphate backbone, and calculating the electric forces that it exerts upon the various entities within the cell, absolutely important for understanding biological mechanics. Another situation that arises quite a bit with long straight rods are quadrupole traps, right? So again, quadrupole traps are quite ubiquitous in many laboratories across the world, especially in the study of trapping single atoms and ions. I know of particular, right, that quadrupole traps are used quite often here in Southern California at laboratories at UCLA and at Caltech. So a lot of motivation there, right, to want to get studied. Obviously not a exhaustive list of things to go through. So we want to know why we care about things when we calculate them. So that's just a little bit of background. So let's go ahead and calculate this electric field a distance d away from the end of this long straight rod. So I reproduced my diagram right here. Again, good calculators, they're not afraid to redraw diagrams. And in particular, right, each diagram should, add a little bit of a layer to your calculation. So got my rod here, length L, distance d, good to go. So now the question is, how do I go about calculating this electric field? Well, like all of these problems that we have been doing, right, in the calculation of electric fields, very and most important first step is to calculate or put down a good coordinate system, right? So what coordinate system do we want to put down here? Well, let's go ahead and take a look, right? Obviously, right, you don't want to do a coordinate system like this, right? So let's draw a little wacky one first and convince ourselves why that's so terrible, right? So I don't want to use this sort of traditional Cartesian XYZ coordinate system because very obviously it doesn't take advantage of the fact that the system has sort of this unidirectional symmetry, right? That everything's happening along a line, right? And if I were to use such a coordinate system over here, right, the calculation of the electric field would require multiple components. Absolutely terrible coordinate system, right? So I think you can guess what type of coordinate system you want. You probably want a coordinate system, right, that does this, right? You want a coordinate system that's oriented with one of the principal directions along the length of the rod, and that would be a good intuition here, right? So we're going to call it to the x direction to the right, and then we're going to call y up. Now, think by looking at the problem, you can convince yourself that the answer for the electric field is going to point to the right, and indeed you would be correct, right? So we don't really care about the y component, but again, it's best in practice to remember that we live in a three-dimensional world, right? So, next question. Where do I put my origin in this problem? Do I want to put my origin over here? Apologies, let me go ahead and make sure to grab all the symbols. Do I want to put it right here at where I want to know the electric field? Do I want to put it at the end of the rod over here, right? Or do I want to put my coordinate system over here at the beginning of the rod? I would argue that you probably want to put your coordinate system right here at the end of the rod, have its origin right there, right? Reason being is that then all values associated with the positions of the relative portions of the rod's charge have positive definitions for their distances to the origin, as opposed to negative distances that would be required over here. And since I'm a positive guy, let's go ahead and pick our origin to be over here. Sound good? Now, in practice, you notice how my diagram got a little bit muddied. Let's remind ourselves that indeed the origin is at the left end of the rod over here, right? However, I'm just going to draw the coordinate system a little bit higher so it doesn't get mucked up in my picture. Sound good? So, how do I calculate the electric field for this particular rod? Well, like we said, we're going to use the principle of linear superposition. And so we're going to use Newton's idea of taking a big problem, right, and then breaking it up into a bunch of much tractable little problems. And in order to do that, we need to remind ourselves of the littlest problem in electric fields. Let's remind ourselves of the electric field of a point charge. So here we go. Formula for the electric field of a point charge goes as follows: 1 over 4 pi epsilon naught. Remind yourselves that is the Coulomb constant, right? You got a charge Q, right? Then you have the following quantity right here, RPS square, R hat PS. So whenever you write down a formula when doing a physics problem, you always want to make sure that you have a diagram to go along with your formula. Again, the great physicist Paul Dirac said, look, you understand something only if you can draw something, right? And he very much was a proponent of physics as geometry and motion, and I very much follow in that same tradition. So let's go ahead and remind ourselves of the definition of the electric field of a point charge. We see a formula, but again, if I don't have a picture to go with it, who the heck cares? So let's go ahead and draw a picture to go with this formula, and from that picture, we'll be able to get deeper intuition on how to calculate our electric field. So again, here's a three-dimensional coordinate system, right? We got a point charge here plus Q. Good. Let me go ahead and clean up that diagram a little bit. So we got plus Q right there. And we got to draw some vectors here, right? So this vector right here, very, very important, right? This vector, nice and good. That vector is R sub S, right? And what is R sub S? This is the source vector, or where is our source of electric field coming from, right? In addition to that, you also got another point, and the other point's over here. Let's call that point P. This point P right here, this is the point of interest. Point of interest is where we want to know the electric field created by this little guy right here. Good. And so there's my RP vector right there. But you look at the formula like, I don't see an RP vector. I don't see an RS vector. I see an RPS vector. What the heck is that? So let's go ahead and draw that one. So we got our nice little RPS vector. Let me pick a nice color here. I think an orange would be nice. And so this vector right here, that goes from source to point of interest, that's RPS right there, right? And the definition mathematically of RPS is this is equal to the RP vector minus the RS vector. In other words, it points from the source to point of interest. So now we have a diagram to go with our formula, which we can then employ this diagram and its logic to calculate the electric field over here of this charged rod. So take a Gandarino right here, right? Remember vertical bars around a vector indicate magnitude, right? So this is the magnitude square or the distance square between the source location and the point of interest location. And R hat PS over here, remember the definition of hat vectors. Let's go ahead and write it down. R hat PS, this is equal to RPS divided by magnitude RPS. It's a unit vector, right? Unit vectors are vectors that have a magnitude of 1. They are dimensionless. And the role of a unit vector is to simply tell you the direction at which a vector points, right? So we see our electric field for a point charge tells us, hey, the electric field of a point charge is equal to the Coulomb constant, the charge of the particle, right, divided by the distance square from the source location to the point of interest location, and finally multiply that by the unit vector that tells us what is the relative direction of the source to the point of interest. So using this logic over here, we're going to take this charged rod over here. Remember this charged rod. has a charge per unit length of lambda. Remember, lambda has units of coulombs per meter. And what we want to say is, okay, given that this rod is charged homogeneously across its body, what electric field does it create at this point that is a distance d away from its end? Now, obviously, we don't know how to calculate the electric field of a long straight rod quite yet, but we do know how to calculate the electric field of a point charge. So let's take advantage of that. Break this rod up into an infinite number of little tiny pieces, calculate the electric field for one of those little tiny pieces, and then add the results all up. So, easy peasy, lemon squeezy. So let's go ahead and get started. So, as previously alluded, let's make a little piece here that we care about. So, I say let's pick this little piece right here. So this little piece right here, we're going to say this little piece has a length of dx, right? Now, again, dx here is not meant to mean change as it normally does in a calculus class. It's meant to mean little or tiny, right? So I got a little tiny chunkarino, right? Now, obviously, I've drawn dx as if it's a finite portion of the rod, but we are assuming this is really, 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 really tiny. So tiny that it effectively has no width whatsoever. So there's dx right there. Fantastic. And now you notice that my diagram's getting a little bit cluttered. So again, good practice. Let's redraw our diagram with the values of interest that we are working on at this particular step so we can proceed on in our calculation. So here's my rod again. Boom. I'm dealing with dx right here. Boom. And now, remember that we said that our origin for our problem was going to be our left-hand side of the rod, right? So we're going to call this point over here the x equal to 0 point, right? That's where my origin is. Fantastic. So, boom. That means my little chunkarino over here, we're going to say its center is a distance x away from the origin. Seems very reasonable. Again, reminder, rod is a length of L, yes. And then we want this point over here a distance d away. And so we want to know the electric field at this particular point, right? At the end of the rod, a distance d away from its end. And what we want to know is, what is the electric field created by this guy? Now, immediately, we can already tell what the electric field of this guy is going to be. Take a gander. Assuming this guy is positive and that lambda is positive, you should remember from your textbooks or your lectures from your professors, right, that positive charges send electric field out away from them. So our approximation here is, because we're using a little tiny chunk here, even though this is a rod that has charge distributed evenly across it, by taking a tiny little chunk, we can pretend to an incredibly high degree of accuracy, in fact, perfect degree of accuracy in the limit that the chunk goes to 0, that this little chunk can be treated as a point charge, right? So all we have to do is take the formula from over here, right? Apply it to our little chunk, add up the electric fields for our little chunks, and we can go ahead and calculate said electric field. So since we're going to treat this chunk as positive, we know it's going to be making a little baby electric field over here that has to be pointing to the right. After all, why does it have to point to the right? Well, let's go ahead and draw a diagram. Well, the reason why it has to point to the right is that this little chunk has to have this RPS vector. Yes? See that right there? Remember, our chunk is source point over here, right, to point of interest over here, where the charge is at, where we want to know the field. Since RPS points to the right, and since our formula for the electric field goes as follows, Coulomb constant, positive, doesn't affect the direction. RPS square doesn't affect the direction because it's also positive. So the only two things that can affect the direction of an electric field, right, are the charge on the particle and the relative positioning of the source point to the point of interest. Since we're assuming that our little chunkarino here, right, has positive charge, right, then that means the direction of the electric field created by this chunk has to follow the direction of the RPS vector. So since RPS points to the right, then r hat PS has to point to the right too. Thus, the electric field created by this little chunk DE has to point to the right as well. Now, using unit vector notation, that makes it pretty straightforward to calculate RPS hat. We see that RPS hat, since its role is only to point, and we can tell from our diagram where it points, RPS hat is just in the x hat direction. Another really important point with regards to this problem, since we're not just considering this dx, right? In fact, we're considering all dx's, so this one, this one, this one, this one. Again, in infinity all the way to the very end, is does dx, which dx we're talking about, affect the direction of the electric field created by that dx? And the answer is no, it doesn't, right? So we know that throughout our entire calculation, our hat PS, regardless of what chunk we're choosing, has to point to the right. A great boon to our work. All right, beautiful. So now we look at our diagram right here, right? And indeed, what we can see is a lot of very useful information, right? Again, the geometry of the problem, apologies. The geometry of the problem is telling us, look, how long is this RPS vector? Because I'm going to need that magnitude. After all, it's present in my electric field formula, right? Well, to get that magnitude, my friends, well, take a look here. I know the entire rod is a length of L, and furthermore, I got to travel a distance d to get to that point of interest. But wait, RPS isn't L plus d. It's all of this distance, right, minus this distance x. So immediately we see from the geometry that magnitude, RPS, this has to be L plus d minus x. And we don't have to worry about any weird sort of minus signs in our magnitude calculation here, friends. The reason being is that we were quite clever and we chose our coordinate system to start over here at x equal to 0. So we know that for all possible dx values right here, right, every single possible dx that I could possibly calculate the electric field for, right, the greatest dx distance to the point of interest in terms of its positioning along the rod, the greatest position it can be is at the L distance, and that would mean we have L plus D minus L, which would give us an RPS equal to D for this last little chunk, and that makes perfect sense. So remember, it's really important that when you're calculating magnitudes of vectors, that you make sure that your formula behaves properly. After all, magnitudes have to be positive definite, i.e. greater than or equal to 0. So if your formula doesn't reflect that, you're going to get into trouble when you do the arithmetic. Okay, so cool. We got our direction of our electric field for our little chunk. We have the distance of our chunk to the point of interest for this particular chunk. Last piece of the puzzle, if we go ahead and take a look at our electric field formula for a point charge is, well, Coulomb constant comes for free. Got these, got this. So now I got to figure out the charge on the chunk. So let's go ahead and do that next. So what is dq? The amount of charge on the chunk. So we're going to use a reasoning through proportionality arguments, right? And again, we're going to be taking advantage of the fact that the charge is distributed evenly along the length of the rod. Well, okay, so what does that mean? Well, friends, let's take a look here. The fact that the charge is evenly distributed along the length of this rod gives us all the information we need to calculate the charge on this little chunk. See, let me explain. If this chunk wasn't infinitesimally small, let's say the chunk was about half the length of the entire rod, well, if the rod had a total charge, right, and that total charge was smeared evenly, right, across the entire length of the rod, right, then we would be forced to conclude that it had half of the charge, right? If the chunkarino was a quarter of the rod's length, again, by that homogeneity of the charge being distributed across the length of the rod, it must consist of a quarter of the charge as well. So we apply that logic to calculate the charge on our little chunkarino as follows, right? Whatever proportion of the total length dx, aka the length of my little chunk, constitutes of the total length of the rod, that same proportion must be equivalent to the amount of charge on that little chunk divided by the total charge. So what we know is that dx over L has to equal total charge on the rod. Apologies, not total charge on the rod, but rather little charge on the chunk divided by total charge on the rod. Or in other words, 1/10 of the length, 1/10 of the charge, right? Half of the length, half of the charge. So we can solve for the little charge on our little chunk, and we find that little charge is Q total divided by L dx. But take a look at the units on Q total over L. Q total over L has units of coulombs charge divided by L meters, right? But that must be what we mean by the linear charge density lambda. So indeed, we get the charge on our little chunkarino, and we get lambda dx. Excellent. So now take a look, right? For our little chunk, right, that we are calculating the electric field for, right, we have its charge, we have its distance square, we have the unit vector that corresponds with it, Coulomb constant comes for free. We can finally write down our expression for the electric field created by this little chunk. Let's go ahead and do that now. So the little electric field created by this little chunkarino, this is 1 over 4 pi epsilon naught lambda dx divided by, let's go over minus r's over distance, L plus d minus x quantity square, right? And then finally, my friends, we got to apply our unit vector here, x hat. And again, we remind ourselves x hat is constant for every single chunk that we have for this rod. All right, beautiful. So again, reminder of using the Leibniz notation. dE here is not meant to indicate change like in our introductory calculus courses, right? dE here is meant to mean little or tiny amount of electric field. So here's the tiny electric field created by this particular tiny chunkarino. Now we want to add up all the electric fields for all the chunks going from x equal to 0 to x equal to L. And the best mathematical operation to do that is going to be our integration symbol. So let's go ahead and do that right now. So please keep in mind, not all integrals need to have an algorithm or procedure, right? Some integrals can simply be done through the power of thought and words alone, right? So what are we going to do? Let's add up all these electric fields, right? And we're adding all these electric fields from our origin, that's where our chunks start at x equal to 0, to x equal to L, where our chunks end. Yes? Again, whatever I do to the left-hand side of my equation, I should also be doing to my right-hand side of my equation. So indeed, I throw in my nice little integration right there. So if I add up all the little electric fields due to all the chunks, I should get the net electric field. So let's go ahead and get that. So we get E net here, that this is equal to, let's go ahead and factor out everything that is independent of the position of the chunk, aka x, right? Well, we know that lambda is independent of position of chunk. We know x hat is independent of position of chunk. We have a 4 pi epsilon naught right there. And then we have our integration over here from x equal to 0 to L of dx all over L plus d minus x quantity square. Okay. Now, this is an integration that should look familiar to you, right? This is going to be a u du sub classic integral. So let's go ahead and do that now, right? And take advantage of the power law that we get as a result of that, right? So, apologies, got a little bit excited, right? I wrote my u when I was still on my x. There we go. Good. So let's keep on going, right? So what substitution are we going to do? We're going to say that u is equal to L plus d minus x, right? Therefore, my integration measure, du, using my substitution, has to equal 0 plus 0 minus dx, right? After all, L plus d, right, aren't changing. They're just parameters, geometric parameters that are used to describe the problem, right? So the only variable here that's changing is what position we are moving to, which chunk we're concerned with, right? So if I change my integration variable using a u du sub, in addition to that, my friends, I must also change the bounds of my integration. So let's go ahead and do that now. So when x is equal to 0, we see that u is equal to L plus d. And when x is equal to L, we see that u is equal to just d only. And again, apologies for the redundancy with the d here, d for distance, and sometimes I'm using d for the integration measure, but c'est la vie. Only so many letters and numbers in the Greek and Latin alphabets, right? So let's move on. So we got all that. We got our integration, substitution. Let's go ahead and clean it up. So we get E net over here is equal to lambda x hat all over 4 pi epsilon naught. Plug in my new variable boundaries, right? So we got L plus d orino over here. Then I have d orino over here. Wherever I see a dx, it has to be replaced with a negative du. So this is a negative du right here, and wherever I see L plus D minus X, I should replace that with the u, so this is a u square. Cool? So let's go ahead and knock out this integral. And remember, we want to make sure after everything is said and done, because we're at the arithmetic part now, that after we do all this arithmetic and algebra and calculus, that our answer matches our intuition. And remind yourself of what our intuition is, right? In that electric field over here at the end, right, better be pointing to the right. So let's go ahead and do that now. All right, this is an integral we should all be able to do. So let's go ahead and do it. So we get lambda x hat all over 4 pi epsilon naught. Antiderivative of u to the negative 2 is negative u to the negative 1. So remember, we have a minus 1 that came from the u du sub, and then we get another minus u to the negative 1 here. And then we got to evaluate at the boundaries, L plus D, and then D over here, right? Those two negatives, though, end up canceling, so you get a boom right there and a boom right there. So go ahead and clean it up. So now that we plug in our boundary terms for our integration, lambda over 4 pi epsilon naught, keep that x hat right there. Then we got two terms over here. Then we have a 1 over D. Pen's losing its mind a little bit. Minus a 1 over L plus D. And this is our electric field, a distance d away from the end of the rod. Now remember though, right, we insisted that this be an electric field has to have the appropriate units, right? And on top of everything else, has to have the appropriate direction too. So let's convince ourselves that is indeed the case, right? So best way to do this is first, let's do a dimensional analysis check. So let's remind ourselves, lambda has units of coulombs per meter. Cool. We know 4 pi epsilon naught. Got to have one of those 4 pi epsilon naughts, right? From the definition of the electric field of a point charge, right? Now, very good question you're going to ask yourself, right? Do I need to know the units on 1 over 4 pi epsilon naught? And the answer is obviously yes if you're doing a calculation. But when it comes to doing these sort of dimensional analysis checks, just know that it carries units. And whatever your final answer is, as long as it contains the units of that piece, right, then you're going to be hunky-dory, funky fresh. So if you go ahead and take a look over here, right, take a look at the formula for the electric field of a point charge, whatever the units on the Coulomb constant are, right, they have to be present. And so if I have a 1 over 4 pi epsilon naught over here, its units, if they're present in my formula too, good. I'm satisfying that part of the electric field formula definition, right? So really the only units I need to check after the Coulomb constant, which again, you could look it up, right? But all I really care about are coulombs per meter square, right? Times Coulomb constant, and boom, electric field. So indeed, I see my lambda over here provides me the coulombs per meter. And then these two terms right here, take a look at them. Well, they're 1 over distances, so they're per meters. So indeed, the lambda combined with the 1 over distances gives me the coulombs per meter square. Couple that with the units of the Coulomb constant. Indeed, it does have the correct units. I can trust this answer. Furthermore, I know that if I am calculating the electric field for this positive rod here, as we assumed it in our calculation, right, then the electric field has to point to the right. So this answer here has to point in the positive x direction. So let's go ahead and verify that, right? So indeed, lambda positive, cool. 4 pi epsilon naught, cool. D is a smaller distance than L plus D, yes? So 1 over D minus 1 over L plus D, this number over here has to be positive. So boom, my electric field points to the right. Another excellent check that I can see and use to trust this answer. Now, beyond just doing dimensional analysis and beyond matching our physical intuition, is there anything else that we can do to check our answer? And the answer is yes, absolutely. There's one more check I can do, and I like to call it the method of extremes. Again, not my verbiage. It's been used several times throughout the community. So the question is, what does my answer look like in an extreme limit where I should already know the answer, right? And so what I mean by extreme limit here is, let's consider the following. What if D much greater than L, okay? So if D was much greater than L, right, what I'm saying here is that I'm really far away from the end of this rod, right? And so now let's put ourselves in this weird mathematical environment, this mathematical universe, where only we exist as sort of this floating brain, right? And we have this charge rod and we want to know its electric field properties, right? Well, if I'm really far away from a charge rod, well, think about when you're really far away from anything, right? So go back to your art classes, right? And think, well, if I'm really far away from something, what happens to the little tiny details of the object? Well, they seem to disappear, right? Again, think in your art class, right? Well, if I want to draw something really far away, right? That means that object, right, its dimensions get scrunched down towards the vanishing point, right? And if we take that same viewpoint with our arithmetic right here, right, with regards to the calculation of the electric field of this finite charge rod, well, think about if I was really far away from a finite charge rod. If I'm really far away from a finite charge rod, then to me, it doesn't look like a rod at all. It should actually look like a point charge, right? So that's what we're going to do right here. We're going to say, if I'm really freaking away from this rod, and again, what does really far away from the rod mean? It means that I'm at a distance such that that distance is much greater than the dimensions of the rod, then I should expect my rod to produce the formula, right, for the electric field of a point charge. So let's see if it does that. So this is going to require a little mathematical finagling. So I'm going to reproduce my formula over here. And let's go ahead and take advantage of the machinery of mathematics and do a lovely calculation right here. Now, what I want to do is I want to take the limit on my answer as d is much, much greater than L, right? Or in other words, when d over L is much, much greater than 1, or vice versa, when L over d is much, much less than 1. Again, I like to do Taylor/Maclaurin series near x equal to 0, right? Whatever expansion I'm doing. So I'm going to take the limit as L over d is approaching 0, right? So in other words, I'm going to ask myself, what does my answer look like when L over d is tiny? Good? Which will be equivalent to being really far away from the rod. All right, so how am I going to do that? Well, again, let's create that ratio. After all, you can't do arithmetic, right? Can't do calculus on dimension-full numbers. You can only do calculus on dimensionless numbers. So from each term in the parentheses, I'm going to factor a 1 over d factor. So that's going to give me a 1 minus a, let's go ahead and take a Gandarino here, right? I'm going to get a 1 plus L over d over here. Now convince yourself that this gives you the same answer. When you distribute the d over here, reproduces that term right there. And when you produce the d over here, indeed it reproduces the L plus d, right? So we're good to go there. All right, so that's pretty neat, but what else can I do with this answer, right? It seems kind of done. Well, remember, what we're really asking ourselves is, what does 1 over 1 plus L over d look like when L over d is approximately equal to 0? Okay? Well, if that's the case, it's equivalent to asking the following. What does 1 over 1 plus x look like when x is approximately equal to 0? And if we squint, right, we see that our x is equal to our L over d. Yes, and so let's go ahead and use the machinery of mathematics, right? Let's go ahead and do a nice Taylor-Maclaurin series here for this function, right? And bada bing, bada boom, we'll be able to see whether indeed it matches our intuition or not, okay? So if that's the case, right, let's remind ourselves of the formula for a Taylor series. We know that f of x near x naught, that this is equal to f at x naught plus f prime at x naught, x minus x naught plus yada, 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 higher order terms, right? And again, as I am only interested in an approximation, right? Since I don't care about those higher order terms, I'm just going to cut it off right here, put a nice little approximation symbol, and only go out to linear order in my Taylor series. In other words, I just want to calculate that thing right there. Okay. So what is that thing? Well, let's go ahead and do it for our function of interest. 1 over 1 plus x, we know this is approximately equal to 1 over 1 plus 0 plus, I got to calculate a derivative here. We'll do that in just a moment, right? But what is the derivative of 1 over 1 plus x? Well, let's go ahead and do that right now quickly. We get d dx on 1 plus x raised to the negative 1. This is equal to, from the power rule, negative 1. Now we got to do a chain rule. 1 plus x raised to the negative 2, and then we get a dx over here. After all, if I take the derivative of 1 plus x with respect to x, right, that just gives me dx, which is 1. Last I checked, this is equal to negative 1 over 1 plus x quantity squared. Excellent, right? So now we have the f prime expression from our Taylor series. Now we just got to plug in a 0 right there. So we get a negative 1 over 1 plus 0 quantity square right here. And then finally we have an x minus 0 over here. So let's go ahead and highlight the relevant terms so we're keeping track of our approximation. So boom, the f of x naught right there, that's that term right there, right? The f prime of x naught term, that's that one right there. And then finally, we have our x minus x naught from our Taylor series definition, and that one right there. And so you see this all simplifies quite neatly. And what we get is 1 over 1 plus x is approximately equal to 1 minus x when x is close to 0. Beautiful, right? So now we can go ahead and apply that approximation over here. And so we can write this thing as 1 minus L over D. And as long as D is much, much larger than L, then we can rest assured that this answer should be at most within a few percentage points of the actual answer. All right, gorgeous. So now we can go ahead and check to see whether our original formula, right, for the electric field, the distance D from a charged finite rod, does indeed approach the point particle approximation when we're really far away from the rod. So let's go ahead and do that now. So we have this thing right here, which we now know we can write this as approximately as x hat. Just going to put that right there. A lambda all over a 4 pi epsilon naught. Then we got a d areno right there. And now we know this thing right here. Notice the squiggles. I know I wasn't a little bit too intentional with the squiggle, but they are indeed there. We know we can write this as 1 minus L over D in our approximate form. Now we see that the ones cancel. See you later, alligator. We see that positive right there, right? And so this all ends up cleaning up to be x hat lambda L all over 4 pi epsilon naught D squared. But remember what lambda times L is. Lambda has units of coulombs per meter. L are the meters of the rod. So this has to be the total charge of the rod divided by 4 pi epsilon naught D squared x hat. And indeed, my friends, right? It produces exactly what we expected. In this limit that we're really far away from the rod, it does produce the point particle approximation as we expected from our art classes. So indeed, friends, we can trust our answer. It passed several tests. Awesome. So that was the electric field and the verification of our calculation of the electric field for our long straight rod, right? And at a distance d away from its end. So now let's go ahead and do this problem right now. What is the electric field at the center of a semicircle of charge spread uniformly across a thin little cross section right there? So let's go ahead and reproduce that problem. Put some nice dashes, make sure we're good to go. And so again, boom, hunky-dory, funky fresh. What's that E field at the center, right? Now, you can pick whatever coordinate system you want. Remember, laws of physics don't care what coordinate system you use. So, in particular, my friends, right, let's go ahead. Well, hold on a sec, right? When I meant to say laws of physics don't care about coordinate system you pick, they don't care about what origin or orientation of coordinate system you pick. Obviously, there are issues that arise should your coordinate system be accelerating versus traveling at constant velocity. But we already, or apologies right here, we will be talking about those in future videos. But when it comes to picking origin and orientation, doesn't matter, right? As long as you're within the same inertial reference frame, right? So I think you can guess where we're going to put the origin in this particular coordinate system, right? We're going to put it smack dab in the center. Why not, right? That's a very, very nice point. So indeed, that's where we're going to put our coordinate system right there, along with the x and y components, right? But you notice that our problem here, right? It doesn't really have XY symmetry. It has polar angle symmetry here, right? So really what would be more appropriate is that we use a polar angle coordinate system. Now, the question is, which polar angle coordinate system do you want to use? Do you want to use the traditional one where you define the polar angle with respect to the positive x direction? Again, it's entirely up to you. As long as you're consistent within your own system, then everything will be okay. Me personally, right, I want to do the problem using this coordinate system. So what I'm going to do is, with respect to the positive y-axis, I'm going to define an angle theta right here, where if I'm at this position, I've subtended an angle theta with respect to positive y. However, if I'm up here, theta is equal to 0. If I'm right here, theta is equal to pi over 2. And if I'm down here, theta is equal to pi. And I'm going to work the problem accordingly based upon that. Furthermore, for this problem, right, I want to pick one chunkarino of interest. Let's go ahead and reproduce my picture. The chunk that I am most interested in is this chunk right here. So let me go ahead and get that one going. So the chunk that I am interested in is this one right here. So you notice I'm making a little pizza slice right here. I want to know the electric field created by this little segment of the arc length ds. Okay. Now, what I want you to notice about ds, right? The length of ds, if you apply the arc length formula, if I call this little angle here d theta, we see that ds has to equal r d theta. Cool. And that the ds chunk, it's located at an angle theta away to the positive y-axis. So if I can figure out the electric field for this chunk, again, I add up all chunks going across all thetas, and once again, hunky-dory, funky fresh. So let's go ahead and finish off our calculation of this electric field at the center of this half ring of charge using Z coordinate system. So here's my chunk. Again, don't be afraid. Redraw those coordinate systems, folks. Redraw your pictures. Otherwise, you're going to get all muddled up. And a clean coordinate system, trust me, pays for itself in time, and time is gold. Okay. So here is a ds. Cool. Here's my little arc length, and I want to know the electric field that ds creates here at the center. So assuming that my half ring is positively charged, I can already guess, right? Take a ganderino here. Let's draw this vector here. Apologies for my terrible dashed line. That's my RPS vector right there. So boom, that has to be my little electric field created by my little chunk as well. So I'm going to do the same procedure that I did before, right? Using the same sort of logic, only I'm going to be a little bit faster now because you can just review that previous logic, right? From the previous exercise where we calculate the electric field a distance d away from the end of the rod, right? So here's what I know. I know that dq for this little chunk has to equal lambda ds, right? Again, ds is the length of the chunk. Lambda is the coulombs per meter of the half ring. So this has to be the total charge contained on the half ring. I know what my RPS vector is for my little chunk. RPS has to just be r long, right? The radius of the ring here, right? As specified in the original premise of the problem. Cool. Now, our hat PS, that one's a little bit more difficult. So let's go ahead and draw that, right? So, reminder, you got my RPS vector here, yes? And we know this angle here is theta. Furthermore, I know r hat PS has to have a magnitude of 1, so I can now use the angle theta to solve for the components of the r hat PS vector. Furthermore, I think you can convince yourself from the symmetry of the problem that the r hat PS vector only has one component that matters. And I think you know which component that is. The r hat PS vector component that matters is the horizontal component. Again, let's do a quick argument, right? Whatever ds is doing up here, right? ds is making a field down and to the left at the center of this ring. However, ds has an evil twin down here, right? And that evil twin, reflected across the positive x-axis of the coordinate system we use, it's going to make that same dE in size, but notice instead of going down and to the left, that one's going to be going up and to the left. So the vertical portions of the electric field contributions from these two ds's that are mirror reflected across the x-axis, right? Those vertical components are going to cancel, and you're only going to be left with the horizontal components, right? So we know with whatever expression we calculate for the electric field for this little chunk, there's only one piece we're really going to have to keep, and that's going to be the piece that corresponds to the x direction, because we know the vertical contributions are going to cancel from this mirror symmetry. But let's go ahead and do that now. So there's r hat ps. There's theta right here, right? So then I know what these side lengths are using a little bit of trig, right? That has to be cosine theta. And this side over here has to be sine theta. Why does that have to be the case? Well, remember, any unit vector has to have a length of 1. And with respect to this theta right here, and because this is a 90-degree triangle, well, this is the adjacent side and this is the opposite side. Now, I said the lengths of these sides, right? I didn't say whether it was a positive contribution or a negative contribution. In fact, if I was to write out RPS hat right now, I know it'd have to look like this. It would have to look like minus cosine theta x hat minus sine theta y hat, right? Remember, trigonometry can only tell you about the side lengths of a triangle, right? It can't tell you whether the sides of the triangle are positive or negative. It can only do that if you specify whatever quadrant you're working in on the unit circle, right? And I've always found that to be exhausting to deal with extra plus and minus signs and worrying about whether I'm in quadrant 1 or quadrant 3. I've always just said, look, I'm just going to use trig to calculate sizes and then I'll put in the signs in myself, right? But whatever works for you, you do that, right? After all, as long as you get to the same answer and the math is sound, you do what you need to do to complete your physics work. Cool. All right, beautiful. So we got our hat PS vector. We got the size of our RPS vector, which is just the magnitude of the radius right here for this half circle. I know how much charge is on this little chunk, so boom, I can calculate my total electric field. I get that dE is equal to 1 over 4 pi epsilon naught lambda ds, but remember ds was equal to r d theta, yes? Then we got to divide it by the total magnitude right here, right? Which was r squared, and then we got to multiply it by our unit vector. So let's go ahead and take that expression over here. Boom, boom, boom. Don't forget those parentheses, friends. And bada bing, bada boom, I got my nice, gorgeous little expression, right, for the total electric field of my half ring at its center, right? And now all I have to do to get the net electric field is add up all these chunks for all allowed thetas in the problem, aka all possible positions on the half ring. But I already said where all those positions were. Based on my coordinate system, my first theta is theta equal to 0. Also, fun little check. If you plug in theta equal to 0, you know this chunk is going to make field down. Does my formula say that? Well, indeed it does, right? Because if I plug in theta equal to 0, right? Ooh, no. I actually made a mistake. See? This is why we always do our checks, my friends, right? Because you notice that I done goofed on these components. If I look at my component here, yes, you see that right there, right? My component right there, right? It needs to be generating field down, right? But then I get in my formula over here, right? And I plug in theta equal to 0, and what does it do to my y component? It kills it, right? That's bad, right? It doesn't match the geometry of the problem. It keeps my x component sound. And then I go back and I see the error in my ways, right? The error in my ways was over here, right? Notice what I did, right? I couldn't fight my mathematics training, right? We were always taught that cosines for x and sines for y, but that's not the way that I set up my problem, right? In fact, here, cosines for y and sines for x. So it turns out that I flipped my stuff. So let's go ahead and fix that. And so it's always really important that when you're doing physics, right, that you do these little mental checks, right, before you proceed on in every step, right? Because if you don't do that, my friends, you can come up with nonsense like I just did, right? And so now, let's regain our composure, our dignity. Let's double check our answers. Bada bing, bada boom. If I'm up here, my field better point down. Indeed, it does. Yes. Let's go ahead and do another mental check. If I'm over here, my field better point where? To the left or into the negative x. Is that indeed the case? Yes, let's check. Cosine of pi over 2, 0. That component goes away. Sine of pi over 2, 1. Gorgeous. Negative x hat. Boom. Done. One more mental check. Let's make sure everything's kosher. If I go to the bottom down here, my friends, we are indeed pointing up. Yes. So it better be that if I plug in pi, my field points up. Sine of pi, 0. Cosine of pi, -1. Negative, positive. Y hat. Dignity composed, regained. We are good to go. Let's continue on with our calculation. So, indeed, I want to add up all these electric fields, right? from all thetas of interest in my problem using my coordinate system. So I want to go from theta equal to 0 to pi, same diff over here, theta equal to 0 to pi. So then we get E net over here. E net is equal to 1 over 4 pi epsilon naught. And let's ask ourselves, what pieces of this integration are independent of the theta angle and which depend on theta? Again, radius doesn't care about theta, so those can factor out. Lambda doesn't care, so let's go ahead and factor out all that junkerino. So we got lambda over r right there. And we got 0 to pi over here, and now we have two integrations, and these are familiar. Sine theta x hat minus cosine theta y hat. Cool. So let's go ahead and think about these two integrations. We can convince ourselves that these two integrals we have to do are going to have the properties that we expect. So here's integral number 2, and here's integral number 1. So let's quickly draw the sine theta function and the cosine theta function. Good, and we're going to draw them from theta equal to 0 to theta equal to pi. So if I draw sine of theta from 0 to pi, this is what sine theta looks like, yeah? It's just that crest right there, right? So apologies for my terrible graph, yeah? So again, that is an integral that will be finite, right? So we're hunky-dory funky fresh there. If I go ahead and draw cosine theta over here, remind yourselves that cosine is just sine phase shifted by pi over 2 rads. We're going to get a very different integration over here, right? Because you're going to get this one over here. So this is pi right here, right? This is theta equal to 0 over here. So indeed, friends, we know the integral for cosine theta is going to come out to be what? 0, because you got a half crest and a half trough of your typical sinusoidal function, while for the sine theta function, right, you got nothing but full crest. So you know that's going to come out finite in its integration. So from this quick graphical argument, we already see component 2. This has to go to 0, so it's only component 1 that matters. Furthermore, we really love our answer, right? Because it matches the original mirror intuition that we came up before. Now the math is just reflecting that same symmetry that I already saw. So indeed, all we got to do is that integral, and we got our net electric field. So let's go ahead and knock it out. So we get E net is equal to, let's go ahead and slap that minus sign out there. So you get a negative x hat lambda over 4 pi epsilon naught r right there, integral from 0 to pi of d theta sine theta. Good. So now that we have all that, integral of sine is what? Well, that has to be negative cosine, right? So then you have negative cosine of theta going from 0 to pi over here, right? And then you got a minus x hat lambda over 4 pi epsilon naught r over here. Don't forget that hat term right there. Boom, E net. Good, good, good. What's cosine of theta at pi? That's negative 1. So the two terms you get here are 1 minus negative 1 right there. Boom, 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 boom. Remember, if you don't make the sound effects, no one's going to take you seriously in life. So you got your 4 right there, you got your 2 right there, and indeed, we get an answer that dimensionally has the right dimensions, has the right direction and everything. We get the E field at the center of our half rod, and friends, we are once again hunky-dory funky fresh. So I hope you found this video. I hope that it helped you to calculate some electric field for charge distributions along some sort of line. So please let me know if you have any questions or concerns in the comments. Otherwise, have a wonderful day calculating and keep the physics fizzing. Take it easy.